Hi guys, so today I will be teaching you, let me just check, okay, it's recording. Alright, today I'll be teaching y'all how to find formal charges in elements of models, right? So, formal charge, let's start off with sulfur dioxide. And we all know that I low-key love sulfur dioxide, right? Okay, 1, 2, 3, 4, 5, right. Alright, so, before we get started, nature really likes to prioritize, elements who have like no formal charge. Like they like to prioritize element 2 as like just like 0 all over, right? But we'll get into more like that later, right? So basically, let's first try to find the formal charge for our lovely little friend sulfur over here, right? Okay, so we all know that sulfur right now has 6 valence electrons, right? To find its formal charge, we have 6 over here, right? 6 minus, right? Look, now let's count the amount of stuff that's around sulfur, right? We have 2 of these things. So 1, 2, 3, 4, 5, right? So it's 5. 6 minus 5 equals 1. So sulfur has a charge of positive 1, right? But no, that's not all, because if that was all, then sulfur would be a positive ion. But let's also find the formal charges of oxygen over here. This oxygen, by the way. Right, so for oxygen, look, oxygen also has 6 valence electrons, surprisingly. So we have 6 minus, now let's count the stuff around it. We have 1, 2, 3, 4, 5, 6. 6 minus 6 equals 0. So oxygen does not have a formal charge, right? Cool. Now finally, we have this other oxygen over here. This other oxygen also has 6 valence electrons. So 6 minus, now we have 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals negative 1. So this oxygen has a formal charge of negative 1. That is awesome. And now overall, the charge of this thing is 0, because negative 1 plus 1 equals 0. So that is really cool. Now let's find another formal charge kind of thing, right? Let's do, for example, let's do H, right? Okay, cool. Oh, and this is also like a positive cation, right? All right, let's find oxygen's formal charge first. Awesome. So this is oxygen I'm talking about. So oxygen, count the number of valence electrons. Oxygen has 6 valence electrons, right? 6 minus 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6 minus 5 equals 1. So just oxygen over here has a charge of positive 1. Wow, that is so awesome. Now let's find a formal charge of hydrogen over here. Luckily, all the hydrogens low-key have the same thing, right? So we only need to count the formal charge for one of these things. Hydrogen over here, let's do this one. Hydrogen has 1 valence electron. 1 minus, oh look, it only has 1. So 1 minus 1 equals 0. So this hydrogen has a formal charge of 0, right? And because this is also the same thing, look, it has a formal charge of 0 and 0, right? 0, 0, 0, and then positive 1. 0 plus 1 equals 1, which means that it also makes sense, because this is also a positive cation of 1. Okay, cool. Now let's get into a little bit harder, right? Let us do, oh yeah, okay. Now we're also going to look into stability of resonance structures. Stability of resonance structures. Let's do RS structures. Cool, right? So, like I said in the beginning of the video, nature likes to minimize formal charge. So formal charge equals minimize, right? Nature does not like formal charge at all, right? And the more formal charge like a molecule has, then the more unstable it's going to become. For example, we have, let me just get rid of this. Okay, for example, we have oxygen, right? Versus oxygen, 1, 2, 3, carbon, 1, now, these are resonance structures because they low-key have the same thing, right? They're like the same thing, except like it's just different ways that they can bond, right? So they're basically resonance structures. Now we're gonna try to see which one is more stable, like which one appears in nature more often, right? So let's first find a formal charge of this one. So oxygen, 6 valence electrons. 6 valence electrons, right? Right. 6 minus 1, 2, 1, 2, 3, 4, 5, 6. 6 minus 6 equals 0. So this oxygen over here has a formal charge of 0, right? let's move on to carbon. This carbon over here. Carbon has 4 valence electrons, right? 4 minus 1, 2, 3, 4. 4 minus 4 equals 0. This carbon also has a formal charge of 0, right? Cool. And now, let's do this oxygen. This oxygen has 6 valence electrons. 6. 1, 2, 3, 4, 5, 6. 6 minus 6 equals 0. So this oxygen also has a formal charge of 0, right? And as we can see, it all evens out at the end because overall this is not an ion, it's not an anion, it's not a cation. So overall it's just a neutral atom, which all measures out because 0 plus 0 plus 0 equals 0, right? Cool. Now let's look at this one. This one I'm talking about, okay? The one I have arrows to. Alright, so let's choose something. Let's purple, right? Let's find out this oxygen first. This oxygen, 6 valence electrons, right? 6 minus 1, 2, 3, 4, 5. 6 minus 5 equals 1, right? So this oxygen has a charge of positive 1. Now let's do one for this carbon over here. Carbon, right? 4 valence electrons. 4 minus 1, 2, 3, 4. 4 minus 4 equals 0, which actually works out because this has a formal charge of 0. And now, what color? Let's do pink. Okay. Let's do this oxygen over here, right? This oxygen has 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals negative 1. So this oxygen has a formal charge of negative 1. And at the end, it does work out because negative 1 plus 0 plus positive 1 equals 0. But as we said, nature likes to minimize formal charge, which means that the molecule with the least amount of formal charge is the most stable. So it would be this one because none of the molecules in that one have a formal charge versus this one which has like 2 formal charges. So y'all know that this is the one that's more likely to be prone in nature and is more stable, right? Cool. Thank you so much for watching my video, and I hope you guys have the best day ever. Let me start doing it. Okay, I'm not gonna draw. Alright. Okay, bye-bye.